Okay, Assalamualaikum warahmatullahi wabarakatuh. This is a recording for chapter 13 of Mechanism of Materials, Buckling of Columns. Okay, the adjectives for this chapter, right, for our course is to understand, first to understand the behavior of columns and concept of critical load and buckling load. Okay, critical load and the buckling failure mode. Okay, and the second one is to determine the axial load needed to buckle a so-called ideal column. Right, we will define what is the ideal column, and then to determine the effective length of a column with various end conditions. Right, the applications for this buckling is you can see some of them, right? I want to draw your attention to this. For instance, you can see that we have a water tank, right? Because it's so huge, we have to put it up on the air, right? Up in the sky, right? So you have to this one will be, of course, it will be very heavy, so you need to support this. So basically you need to put a couple of columns, right? One, two, for instance, right? And with various end conditions like these kind of end conditions. So this is how actually the engineers design the support for this water tank, right? And some of these failure mode due to buckling, like this column. Okay, you can see that it buckles I mean, along the line, right? This one. Mm. So this is the buckling failure mode, right? And then again, long columns, a long slender member that supports a roof, something like that. So, for instance, right? Okay, now we define what is the critical load, critical load. Okay, so first, before we define critical load, let's define what is column. Columns, okay, columns is long slender members subjected to an axial compressive force. As simple as this example, right? So you have a slender, okay, long slender member subjected to axial, okay, axial compressive force. Axial compressive force means that the force is applied axially along the axis of the member, right? So if you apply load like this, right? So what happens is that you will have, okay, initially it's straight, right? So you have the lateral deflection, new. So if this happens, we call this as buckling, right? And the maximum axial load, okay, that this column can support without buckling, I mean on the verge of buckling, without buckling, we call it as the critical load. If you apply load P, which is less than critical, which is P critical, right? So the member won't buckle; it will remain straight, right? But if you apply load beyond P critical, then you will have this lateral displacement of V, okay? Okay, sorry, this lateral deflection of V, which means that now the column starts to buckle, right? And this is the model, right? How do we explain, or we want to explain, but model this kind of phenomenon. So basically, you divide into two, okay, two parts of this long column. You apply the spring, right, and then you apply the P, and then you have this lateral deflection of delta, and of course the P in this case it buckles this way. The P is sorry, not the P, the spring is compressed, right? And then you have the reaction E of this from the spring. I mean, this is the idealized. I mean, it's not the real one. This is just the model. Okay, from this model, we can see that the relation of P, the P itself, is independent of theta, of the angle. Okay, of this deflection angle. All right, the P is independent of deflection angle. Okay, now let's go to ideal column. What is ideal column? The column is assumed is defined to be ideal. Of course, there is no ideal column actually in reality. But when we say that this column is ideal, we assume that it is perfectly straight before we load. Okay. If there is no load for this column, you don't apply any load, any axial load, it is perfectly straight, right? And the second one, second assumption is it is made of homogeneous material. What does it mean by homogeneous material? The material throughout the volume is has the same properties, right? At any points and any locations throughout the material, throughout the body, throughout the volume, it has the homogeneous properties, same properties, right? And the loads are applied throughout the centroid of the cross section. For instance, if it is circle, right, circular cross section, it will be applied at the center of the circle itself, right? So centroid, okay. So you need to know where is the centroid, of course, and you assume that for ideal column, the axial load is applied throughout the centroid. Not, I mean, it will. There is a discussion, not in this course, by the way. When you have eccentricity, which means that you don't apply at the centroid, and what happened? I mean, that's what will happen. In this case, we assume everything to be ideal, right? But actually, it's not ideal. Okay. Okay. Now, let's look at this. The behavior of this ideal column, right? If you apply the load P, which is less than the critical load of that material, of that column, so the column will remain straight, which means that if you apply the load, then this load P, right, and this P is less than P critical for this column, so this column will remain straight, right? But once you apply the load, actually you can test this with your ruler, okay? Apply the load which is actually bigger than critical load, that it starts to buckle, and this is defined by this equation. So actually here it starts with this one. You remember this one from chapter 12, right? Deflection of beam, where you have the second derivative of the deflection, right? Times the I equals to the moment, right? And then if you solve this, and then you will end up, and then you put the boundary condition, you will end up with this kind of, the ratio of P is n squared pi squared EI n pi squared, where n equals to 1 over 1, 2, and 3. And of course, the lowest one will be n equals to 1. So your critical buckling load is pi squared EI over L squared. Okay. Of course, when you change, okay, this is your critical buckling load. You will see later on, okay, that actually this one is for the pin and pin ends, right? So don't just quote this. This is for pin and pin. If you have different conditions, so basically it will have different types of supports. Then basically you will have different, here you have K elsewhere. We'll see that later on, okay? So if you have this P critical like this, so you can change this to critical buckling stress, okay, this, right, just divided by area, okay. If you do that, then you will end up with this equation, this expression, pi squared E over KL over R, all of 2, right? And this R is radius of gyration, right, from statics chapter 10, right? When you learn about moment of inertia, you learn about this radius of gyration as well, right? And then L over R, okay, we call this as the slenderness ratio, okay? What does it mean by that? For instance, you have a column like this. This is L, okay? This is to R, all right? 2 radius, R to R, L, okay? R is the radius, for instance, okay? Of course, not everything is circular, right? So that's why you need the radius of gyration. So you can cover this you can define a radius of gyration for any cross section, right? Because you divide I with A, and then you square root that one, then you find the root, then that's your radius of gyration, okay? So if you divide L over R, then you get your slender ratio. Okay, so here what you can see, okay, look at this graph, right? for these two types of materials. One is the structural steel, and then one is aluminum alloy. Okay, where the structural steel has a yield strength of 250 megapascal, while the aluminum alloy has a yield strength of 190 megapascal. Okay, so on the ordinate axis, you have the critical buckling load, sigma critical, and on the abscissa axis or x-axis, you have the L over R, which is in the threshold. So what you can, okay, engineers have plotted this, right? What do we see here? We see that, okay, the critical buckling load, for instance, you see the critical buckling load when the slenderness ratio is 89, okay, for structural steel, the critical buckling load is 250. Can you see the graph, right? What does it mean by this? It simply means if, let's say, the slenderness ratio L over R, okay, L over R of your column is higher, okay, more than 89, higher than 89, what will happen? Your critical buckling load is lower than 250. For instance, if it is 100, right? So it will be here, which is lower than 250. So why this is important to understand? Because if that happens, for instance, there's a ratio of 100, and then you get the critical buckling load of 100, for instance, 170 megapascal, for instance, okay, here. So it means that if you apply load, okay, the column will buckle first. It doesn't fail due to yield strength. It buckles first, not change yield strength first. Okay. If let's say your slenderness ratio is less than that, then that's fine. Okay. Less than 89, then that's fine, because the critical buckling load is higher than 250. So it will reach the sigma y first, not the buckling first. Okay. Same goes to aluminum alloy. Okay, in this case, the critical buckling load, the slenderness ratio of 60.5 will reach the critical buckling stress of 190, right? Here. Okay, what does it mean by that? For instance, if for this aluminum alloy, okay, the second curve, if you apply, if the design has the slenderness ratio of 100, so the critical buckling stress will be like, for instance, 60 or 50, I don't know, okay, which is less than 190. Again, it means that in this case, okay, with this higher L over R than this 60.5, in this case, the aluminum alloy, that aluminum alloy column will buckle first, not yielding first. All right. But if let's say it is less than 60.5, for instance, it is 50, right? So the critical buckling stress is higher than 190, isn't it? So what will happen? If you load that kind of column, it will reach the yield strength first, and then, okay, this is important because we want to determine later on. We have to see which one comes first, which failure mode comes first, whether it's buckling, okay, or actually it is yielding. Yielding is the same like what we have done before, right? So let's look at this example. Okay, so you have this A36 steel. For this kind of cross section, okay, the member of W200 times 46, right? You have this data sheet for this W200 times 46, which is a wide flange beam, right? And then you have a pin connected column. So basically, it is pin and pin right here. And then the question asks you to determine the largest axial load, okay, the support for it either begins to buckle or still yield. So again, let's say you have two modes of failure in this case for the column. Okay, it's either it buckles that we are discussing now, or it yields like what we discussed previously, right? So for this W200 times 46, you have this kind of I beam, right? W because it's a wide flange beam. Flange is this. Okay, I hope you understand by now because you have seen this in chapter 6 and 7 and 8 as well, of course, right? So here you define XX like this, YY like this. Actually, you can define any way, but the one in your data sheet, they define, for instance, if you have this kind of white flange called white flange beam, right? So this is XX, right? And the other one is YY. That's why define XX like this, YY like this. Okay. So from Appendix B, which is actually from your textbook, okay, you'll see that for this W200 times 46 white flange beam, right? Remember, you have it has the area of this, and the IXX is this, and IYY is this. Again, please understand which one is XS and Y. In this case, this is X and X, right? Look at the table, this table, right? All right, and then from this, when you compare IX and IYY here, we see that the IYY is lesser, isn't it? IY is less than IX. Can you see that? What do you mean by that? It means that actually about this y-axis, okay, this beam, okay, about this y-axis, the beam is weaker than about the x-axis. That's why it has lower I. Okay, so we will check the one which is weaker axis. Okay, so we check about the weaker axis, which is the y axis, and we just simply put the critical, we put into the equation the critical buckling load of pi squared ER over L squared. Okay, and then E is 200 gigapascal, right, for the 86 steel. 86 steel, right? I is IYY, right? Because this IYY is the weaker axis, isn't it? And the L is the length, which is 4 meters. All right, and then you will get your critical buckling load of 1887.6 kN. By the way, like I said, don't simply use this formula, all right? Because this formula actually depends on the boundary your support types. In this case, it is pin connected column, which means that it is pin here, it is pin here. So basically, that's why you can use this formula. Otherwise, don't simply use that, okay? Because actually the correct, the comprehensive formula is KL squared, and K is something that we're going to talk later on, okay? And then once you got this critical buckling load, so you have to check what is the resulting compressive stress. Critical, we call it critical buckling stress, right? Just divide critical with the area from the appendix B, okay, for this white flange beam. So you have, or column actually, you have the critical buckling stress of 320.5 megapascal. All right. So if you have to check this against 86 again, against 886 steel, for 886 steel, the sigma y, the yield strength of 86 steel is 250 megapascal. 250 megapascal, all right? So what does it mean by this? Sigma y equals to 250 megapascal, while sigma critical equals to 330.5 megapascal. What does it mean by that? It means that this material, this column will fail in which mode first? It will fail due to yielding first, right? Because yielding here, in this case, is lower than the critical, right? So that's why now your critical largest axial load that can be applied, okay, which it can support before it either begins to buckle or the steel yields. So the one which is the largest load will be checked against the yield strength, not the critical buckling stress, right? Why? Because here the critical the yield strength is lower, so you need to use the lower one, and then you got your the maximum, the largest load that can be applied without buckling, without yielding, which is 1.47 megameter, right? Okay, now we go to the last part. columns having various end conditions, okay, columns, but now you have various different end conditions. Okay, so now we consider cantilevered column, which is fixed at base and free at the top. For instance, like this, fixed here, right, and free here, all right. Now again, if you start by using the EI of the and then times second derivative of nu with respect to x equals to m, then you got this. You solve this, put one condition and everything, and then you will end up with this. P critical equals to pi squared EI over 4L squared. You realize the difference between this and the previous one that we have seen? Previous one, it was pi squared EI over L squared, right? There is no 4 here. So that's why actually, if you do this for any types, different support types, right? So you will have the general formula of critical buckling load to be pi squared EI over KL all squared, right? And K is the effective length factor depending on the support conditions, right? Previously, K equals to 1, right? That's why it is pi squared EI over L squared, right? K equals to 1. Why? Because it's pin and pin. In this case, K is not 4, is 2. Okay? Because 2L all squared becomes 4L squared. Right? Why this K equals to 2 in this case? Because this is a fixed and free. Okay? So for various and condition, here we give 4 for you. If it is pin and pin, okay, pin and pin, like the first one that we did, the K equals to 1. All right. So what does it mean by that? Your P critical will be pi squared EI over L squared, as simple as that, isn't it? For the second one, okay, let's go to the third one first. Okay, if it is fixed and fixed like this, and you apply the load, now the K, sorry. Let's go to the second one. Mistake. If it is fixed, right, and free, so K equals to 2, fixed and free ends. What does it mean by that? If you put into the equation, then it becomes pi squared EI over 4L squared, right? Like this. Here, if it is fixed and fixed, okay, fixed and fixed, so your K is half, right? And if it is fixed and pin, pin and fixed, so the K is 0.7. Okay, actually it's not to be more accurate, actually it's not 0.7, it's 1 over root 2, right? Is it 1 over 2.7? Isn't it? Yes, 1 over, so this is actually 1 over root 2. That's why it is 0.7, right? So of course there are some more other various end conditions, okay, other end conditions, but these 4 are the most common ones, right? Okay, now we go to the next example. So again, you have this kind of white flange column, or beam, it says the column, right? Okay, you see that the white flange here, white flange, I shape, so-called I shape, right? Total length is 8 meter, 4 and 4, right? And it is fixed at its ends as shown in this figure. Okay, its load carrying capacity is increased by bracing it about YY axis, right? Which is the weak axis using the struts that are assumed to be perpendicular to its mid height. Okay. So about this example, try to read this. Okay, what you have here is you have different IXX, IYY with different types of support at XX and YY, and then you compare them and you see which one will buckle first. Okay, and then you have F13.1, F13.2, and F13.5 will be in your tutorial, right? I will post the tutorial for these problems. Okay. And then we go to the next part, which is secant formula. Actually, it's not in the objectives, right? But secant formula, I just want to say that in this case, actually, what happened is you don't use ideal column, all right? In actual, there is no such thing as ideal column. You just assume the column to be ideal, okay? And in fact, like I said, there is no ideal column. In reality, it's not ideal. That's what I mean. So secant formula discusses on how, if it is non-ideal, I mean in reality that's not ideal, right? So how do you explain the eccentricity? Where is the location? You apply the load is not at the centroid. So what happened to to the deflection? All right. So you have this relation. Sorry, not this relation. This relation. Secant formula is this relation of this eccentricity, right? And then, yeah, but we're not going to discuss here. It's just to let you know we're actually uh, column. There is no, the real column is not ideal, okay? And secant formula describes when it is not ideal, what happens, right? Okay, and then that's the end for chapter 3. Please watch the tutorial videos as well. Thank you.